In the last video on step response, we set up the differential equation that describes our circuit, and we found that it was a non-homogeneous equation. And now we're going to follow through on the strategy of solving it with a forced response plus a natural response. So here's two copies of our circuit, and we're going to, on the top one here, we're going to solve for the natural response. And on the bottom one, we'll use that one for the forced response. All right, let's go to work on the natural. Now, to do a natural response, what we do is we set the initial conditions to whatever they were for the original circuit. So that involves some Q and a V0, a V0 on the capacitor. So let's just draw in quick. Let's draw in our Q. There's some Q here, and there'll be a plus or minus V0 on the capacitor. Now, the other thing we do is for the inputs, we set the inputs to 0 to do the natural response. And how do you do that? Our input here is a voltage source, and we're going to suppress the voltage source. That's how we do it with superposition. When you suppress a voltage source, what you do is you set the voltage to 0. And that means that's the same as creating a short circuit for this. So for the natural response, we're going to take out our voltage source and replace it with a short circuit like this. So this circuit now is identical to the circuit that we used for the natural response. So if you haven't seen that video on how to solve for the natural response, this would be a good time to go look at that. What I'm going to do now is just write down the answer from that. This will be plus or minus, we'll call this V natural, and that equals some K natural times e to the minus t over RC. This is the natural response of an RC circuit. So I'll put a square around that so we can remember it. And I've left a constant in here, and we'll work out what this constant is a little bit later. Okay, so now let's move on and do the forced response for this circuit. And for the forced response, we remember the initial conditions are set to 0. So that means the Q equals 0 here. And that means that the initial V is 0. I'll just write in 0. So that's what it means to set the initial conditions to 0. And the inputs are equal to, we use the inputs this time, the input is equal to Vs. And in particular, the input is equal to Vs. We're going to solve the forced response after time equals 0. So that means that the input is Vs, capital Vs. And as a reminder, what we're trying to solve here is the differential equation from the previous screen, and that is C times dV dt, and I'll put a forced in here, plus 1 over R times V forced equals 1 over R times Vs. I could plug in capital Vs here because we're trying to solve this for this initial condition. So this is our differential equation for the forced response. And we're going to take a strategy here that's like we did with the natural response, is we're going to guess at an answer for Vf and then plug it into this differential equation, this non-homogeneous differential equation, and we're going to see if it works. And a good guess here is to guess something that looks like the input. So a good guess is going to be some function that looks like Vs. And Vs looks like what? Vs looks like, over here, Vs looks like a constant. So we're going to make a guess here that the forced response looks like some constant. And we'll call that Kf. The way we test our guess is to plug it back into here. Plug it back into the differential equation. So I'm going to do that. All right? So we'll get C times the derivative of Kf with respect to time plus 1 over R K sub F equals 1 over R times Vs. All right, now here's the interesting thing that happens next. What's the derivative of a constant with respect to time? That goes to 0. So this first leading term here of our differential equation goes to 0. And now I'm left with kf times 1 over r equals vs times 1 over r. So that makes kf equal to vs. So I'll tuck this in here. Our forced response, vf, equals vs. So now I have our natural response right here. And in this square, we have our forced response. The forced response is just a constant Vs. So now we're ready to come up with our total response. We'll call that V, capital T. The total response is equal to the natural response plus the forced response. So now we're using our principle of superposition. Okay, Vt equals K, some constant, times e to the minus t over Rc. And let's add the forced response, and the forced response is right here. It's Vs. And we're getting close. The only thing we have left is we have to figure out this value now. We have to figure out the gain factor in front of the exponential term of the natural response. Now, the way we go after that is we would know this if we knew what Vs is, and we do. It's called Vs. If we knew Vt at some time, we could plug in two values here. We could plug in a Vt and a t. And one of the most convenient times to know this, if we set t equal to 0, and we know that V total at time equals 0 is what? It's basically, let me roll it up here a little bit. Let's go backwards a little bit. Let me go back here and use this diagram again. This was the force response. So we're not going to use that right now. We're going to use, this is now the total circuit all assembled together. And we have to figure out what is the actual initial charge on here. And if we recall, the initial charge on here was V naught. That was this value here just before time equals 0. This was the value of the voltage on that capacitor. So I can fill that in here, V naught. All right, let's go back to our total solution and plug in these two values. Time is 0 and Vt equals V naught. So that looks like V naught equals natural constant times e to the minus 0 over Rc plus Vs. And let's solve for Kn. Kn equals, this term is e to the 0 is 1. So this term goes to 1. So that says that it's Kn plus Vs is this side. And I can write down here V naught minus Vs. So now I've solved for K. And we can finish our total response. We can say the total response is Vt equals K sub n, which is V naught minus Vs e to the minus t over Rc and plus Vs. And that is the total response of our circuit. And we solved that in two steps. First we did the natural, and then we did the forced. And we added them together and worked out the last constant, whatever the constant was, and there's our answer. So in the next video, we'll do an explicit example with values for R and C in the step, and we'll see what it actually looks like.